Hello, my name is Victor Engelmann, and in this video I'm going to show you how to write your own operating system. But first things first, I want to thank two websites, osdev.org and lowlevel.eu. These are two websites which talk about writing your own operating system, and I have learned a lot there. Before we start, I should tell you what my specs are. So if you want to follow what I'm doing, it's probably the best idea to also use Linux Mint 17. And I guess the rest should probably work out no matter what processor you're using. The software you will need for this is you will need the GNU compiler collection C++ compiler, G++, the GNU assembler, AS, and a package called libc6dev i386. So from what I've just said, you probably already deduced that I'm going to write this operating system in C++. And, well, many people prefer to write their operating systems in C. And, okay, C is fast, and that's an advantage. But on the other hand, I prefer object-oriented programming. So I think really procedural programming is a thing of the past. Now, granted, you can do quasi-object-oriented programming in C, but to me it just feels unnatural and kind of hackish, and I don't think C is really designed for it. So I really think C++ is the best compromise between the performance of on the one side and modern programming paradigms on the other hand. So before we start, we should talk about what happens when you start your computer. So let's see. So here's your main board. And on your main board you have your BIOS. And attached to your main board you have your hard drive. Okay, this looks more like an iPod. And also on your main board you have your CPU. Okay? And I guess you already know a little bit of assembler, because I don't think it's a good idea to start writing an operating system if you don't know any assembler at all. But if you know a little bit assembler, you know that a CPU has several registers, and we'll be dealing with the registers AX, BX, the stack pointer, and it also has an instruction pointer. Okay? Now, when you start your computer, then the main board will do the following. It will take the data from the BIOS. It contains really basically something like assembler code. So it's your firmware. And it copies the content from the BIOS to the RAM. Okay, here's your RAM. Okay, so it copies the firmware from the BIOS to the RAM. Now you have it here. Here's the firmware. And then it tells the processor, okay, please put your instruction pointer into this position. And this now means that the CPU will read the instruction that is there and execute it. Okay, so basically what this does is the CPU will now execute the firmware. The firmware will then tell the CPU, hello CPU, please talk to the hard drive, and it will talk to the hard drive relatively low level. I don't think it knows partition tables or file systems, so it will just look in the raw data. The first, I don't know, maybe 2 megabytes of the hard drive is the boot sector or master boot record. And well, this will then be loaded also into the RAM. This is a bootloader. In this tutorial, we will be using the bootloader grub. Okay, so many people say if you write your own operating system, you also have to write your own bootloader, and I kind of agree with that, but trust me, you are not at the point where you are able to write your own bootloader. Okay, so we'll just stick with the grub bootloader for now. Yeah, this is loaded from the master boot record into the RAM, and then the firmware will just basically proceed and tell the CPU to jump into this bootloader. Okay, so now the CPU will execute the bootloader. The bootloader is a bit more sophisticated. It knows about partition tables and file systems, so it can deal with directory structures. So it will be able to go to the second partition and look into the directory /boot /grub /grub.cfg. So it will load this file, and then it will read this file, and it will contain some menu entries which contain information about which operating system is where on the hard drive. Okay, so if you check this file out, you will find several entries. For example, when we look into my grub CFG later, you will see entries for Windows and for Linux Mint and other things. Okay, so now the bootloader will just print this list of operating systems on your screen. And now with your arrow keys, you can select one of these operating systems. Let's say you selected this one. And then grub will say, okay, this operating system, it's the one on maybe on the third partition here. So, and now I need to load /boot /kernel.bin, for example. So it will load this file. Might be here. So then it will copy this kernel bin also to the RAM. Now the kernel bin is loaded in the RAM, and then it will tell the CPU to jump into the kernel. Okay, and this is the point where we come into play. Okay, so this is the point at which our code will start to be executed. This is the point where our entry point will be called of our kernel. Okay, we have a big problem at this point. The bootloader will not set this register, the stack pointer. And this is a big problem because C++ programs expect the stack pointer to be set before they start running. Okay. So what we will have to do now is we have to write two different files. One assembler file, which we will call loader.s. And this will basically just set the stack pointer and then jump into the other file, which is kernel.cpp. Okay? So, yeah. The loader.s file will be compiled using the GNU assembler as, and then we'll get a file called loader.o. And the kernel CPP will be compiled with G++. And this will create a file called kernel.o. So the problem now is we have two different object files from two different programming languages. And now they need to be combined into one common file. Okay, and to do this, we will use a program called LD, which is a linker, and this will combine these two files and give us the file kernel.bin. Okay, and this is the file that we will then just put into the boot directory, and we'll have to write an entry in the grub CFG so that the bootloader can find it. Okay. So one thing I should mention, when you start your computer, even I mean it's 2016 now. Okay, 64-bit processors are the standard nowadays, but even today, when you start your computer, the CPU will start out in a 32-bit compatibility mode. Okay, so at the start of the kernel, we are in a 32-bit mode, and to be honest, I don't actually even know how to switch to 64-bit mode, and so we'll just make all this stuff 32-bit, so it will be compatible to the mode that the CPU is in at the startup of the program. Okay. Okay, so let's start. So here's an empty directory, and I will create 4 files. Loader.s, as I've told you. Then kernel cpp. Linker.ld. And a makefile. Okay, I will edit this in a program called Kate. Okay, so I assume you know a little bit about makefiles, and I'm not going to teach you a lot about it. I'll just put some usual stuff here, like to create a .o file from a .cpp file. What do we do? Well, we call g++ with some parameters which will be taken from a variable. And I will, well, for the 32-bit mode, this will be one of the parameters. The output should be the target file, and we want to compile the input file like this. Okay. Now, if we want to create a .o file from a .s file, how do we do that? Well, we use the assembler as with as params. The output file is the target file, and we will be using the input file as input file. Okay, and this variable as params we set just to 32-bit. Okay. Now, in the end, it's we want to create the file mykernel.bin, and this will depend on the linker.ld file and also the object files. Okay, and the object files are just loader.o and kernel.o. Okay. Okay, how do we create that? Using ld with ld parameters. As input file, we will use the linker ld, so the first of the dependent files. We will create the target file, and as inputs we will use all the object files. Okay. And in the end, when the my kernel bin is completed, then we want to be able to install it. So this depends on my kernel .bin, and it will just sudo cp the kernel bin to /boot my kernel bin. Okay, so oh wait, I've forgotten to declare the variable ld params. Okay, so this isn't all we have to do in the make file, but this should be sufficient for now. So let's look into the kernel CPP. Yeah, we will just have some function. We can call it whatever we want. I will call it kernel main. And let's say it's supposed to just print out a message Okay. So at the end of this function, we don't want this program to stop in a way. I mean, what does it mean that a kernel stops? You know, it doesn't really even make sense to talk about it. So at the end, we will just go into an infinite loop. Okay. So this is supposed to be our what our kernel does. Now let's look at the loader S. So as I've told you, there's a problem that the stack pointer isn't set to anything at the startup of the when the bootloader is done. So what we'll have to is section.text. You know, this is this should be familiar when you have when you are when you know some assembler. Extern kernel main. So this is so here I tell the assembler that there is going to be something called kernel main. So it is this function, and we want to be able to jump into that. So we are telling the assembler here, if we want to call kernel main, just assume it will be there. The linker will take care of it. Okay, so then we need this is the program entry point. nothing spectacular also if you know a little bit of assembler. And what we will do now is, the first thing we will do is we will just set the stack pointer. And what do we set it to? Well, to something, to some pointer for some stack. Okay, so where is that? This isn't declared yet. And we will declare that at the end of the file in its own section, which we will call BSS. And yeah, this is just the position for the kernel stack. Okay. So this is the pointer where we set the ESP register to. Okay. So now we have another problem. So let's say this is a kernel. Okay. Okay, so here's maybe here's the instruction that sets the ESP, but where does it set it? Well, it would set it relatively close by, and that would be a problem because well, the stack is going to the left, so when we push just a few things there, we will be overwriting stuff, and it will be not a good idea. Okay. So what we will do now is we will just put some empty space in between and then have this kernel stack pointer behind this space. Okay, so so that we set the kernel stack pointer such that there's we will just use 2 megabytes of space in between, okay? So this can be done using dot space 2 times 1024 times 1024. So this is 2 megabyte. Okay, so now the stack pointer is set to something sane. And as I've told you, at the end of the kernel main, we will be going into an infinite loop. So when we jump into the kernel main, it's not supposed to ever come out of that again, but just to make sure, we'll just have some another infinite loop after that. So okay, so this is another infinite loop. Okay, now the next big problem we have is that the bootloader will not recognize this as a kernel, because a bootloader, when the bootloader looks at this file, the kernel bin, it will look for a so-called magic number in that file, and if it's not there, it will not assume that it will not believe that this is actually a kernel. So what we have to do now is we need to put this magic number in there. Okay? So yeah. So this magic number is the hexadecimal number 0x1 BAD B002. So we need to put that into this file so that the bootloader will accept it as a kernel. Okay, so let's do that. First, I will just store this in a compiler variable, so this will not actually be put in the resulting .o file. Also, we need to set some flags. This is also just for the bootloader. And we also need to set a checksum. To minus the magic number plus flags. Okay. And now we have to actually put these into the .o file. So we do this by using a section. Section Multiboot. And it contains just these variables. Okay. Okay, so this should actually work already. But there's another thing. When the bootloader has decided, okay, this is a kernel, I will load it and I want to jump in this, it actually, before it does that, it actually stores some informations on somewhere in the RAM. So at some point there's going to be this so-called multiboot structure. So multiboot structure containing some information, for example, the size of your RAM would be stored in there. And I think it's not a bad idea to really use that. So, I mean, why not have that? If the bootloader gives us that, why not take it? So what does the bootloader do? Well, it creates a structure, and then it stores a pointer to that in the AX register. Okay? So, and also it copies the magic number into the BX register. Okay? This is also what it does. So I think it's not a bad idea to just take these informations. As I said, why not? So so just before we call the kernel main, we just push AX and push BX. And now we, in the kernel main, we have to accept this information, you know. So you will find online files like multiboot.h from the GNU project. You can use that to store to accept this multiboot structure. For now, I will just use a void pointer. So that the compiler won't bother us. and it also gives us the magic number as unsigned integer. Okay, actually I don't know why we should be interested in having the magic number again, but maybe for some error checking or whatever, let's just have it there. It doesn't hurt us. So, so this loader.s should already work. Let's try this out. Yes, there is the loader.o. Wonderful. Okay. And we can also try to compile the kernel, but it won't work. But why doesn't it work? Well, it says printf was not declared. Okay, so this should not surprise you because I didn't include standard I/O or whatever, you know, the usual files for the writing of text to the screen. Now the problem with that is we are at this point we are outside of an operating system. You know, the regular printf that you can include with standard I/O or whatever. It's inside a dynamic library. So usually when you write a program, you have your operating system around it, like say Linux. And here's your program inside of that environment. Here's your program. And when you call printf, well, when you start your program, Linux will see, okay, your program is using stuff from, like printf, stuff from the glibc library, the standard library for C programs. So when you start your program inside Linux, then Linux will use the dynamic linking to load glibc and connect your program to glibc. Now, problem one, we don't have glibc for our operating system yet, and we also don't have an operating system around us which connects this for us. So we have no dynamic linking, we have no libraries. We have nothing. We don't have dynamic memory management, so we cannot use malloc and free, and we have nothing to write something on the screen. Nothing, absolutely nothing is there. Okay, everything we want to do, we have to write ourselves. Okay, so what we have to do now is we have to write our own printf. Okay, and okay, this is probably, if you want to write a complete printf, this will be madness probably. But we will have a small, simple version of printf. Yeah, how do we write it? It's basically you just need to know how this works. So if this is your RAM and this is your screen, there is a specific memory location, and it's the location with the hexadecimal address 0xb8000. And whatever you write here will be put on the screen by the graphics card. Okay, So if you write an A here and a B here, then the graphics card will write AB here. The question is, what is with these bytes in between? Well, they are for color information. Okay, so yeah, this byte has 4 high bits and 4 low bits, and they are for the foreground and background color of the character. Okay, but we will not be using this at this point, so we will just use black and white text. Okay. A good thing though is that on your program startup, these bytes in between already have same values in them, so you don't have to set this color explicitly just to have white text on black background. Okay, so this combination black background white text is already in there from the beginning. We just have to make sure that we don't overwrite that. Okay, so how do we do that? So we will have a pointer to this. We will store a pointer to this memory location, unsigned short pointer. Okay, and now we will just have to copy the string to this location. Okay. Okay, so this would already work, but what we are doing now is I've declared this as an array of unsigned short, so of 2 bytes at once. So these 2 bytes are grouped together, these 2 bytes are grouped together, and so on. So this is element 0, 1, 2, and so on. So if I do it like this, there's the problem that if I set it like this, I'm overwriting this high byte. So I need to stop doing that. How do I do that? Well, I'll just copy the high byte that has been there before. Video memory I, but only the high byte, and combine that with the string. Okay, I think this should work now. So let's see. Oops, little mistake. Okay, we get a normal warning when you convert strings to char pointers. We will just ignore that. But yeah, we have another problem. So, as I've told you, we are not inside a Linux environment where there is a glibc library and a lot of other things that Linux would deal with for us, like, for example, exception handling and dynamic memory management and exception handling and stuff, which is done by Linux. And yeah, the compiler would usually assume, well, there is an operating system, I can just do this and that. But if we try to run this outside of an operating system, it just will not work. So what we have to do is we need to tell the compiler, don't assume that there is a glibc. Don't assume that there is something that deals with exceptions and that gives you an answer to the interrupt for dynamic memory management and stuff. So we do that in the make file. So we just need to give G++ additional parameters. Okay, what are the additional parameters? We need f no use c x a at exit. This has to do with memory management. No stdlib, so we don't have a glibc. F no built-in. F no runtime type identification. F no exceptions. And another one, F no leading underscore. So this has to do with the naming of the sections on in the resulting .o file. If we didn't have that, then the loader would not be able to call kernel main. It would have to be underscore kernel main, but that's just a minor thing. So okay. So then let's look at the linker. How do we link this now? I mean, if we had different files from the same programming language, we could tell the compiler to deal with that for us. But when we have files from different compilers, then we can't do that, and we have to take care of it ourselves. And I'll admit, I'm not an expert with dealing with the linker. I usually compile stuff, all stuff within one language. So I usually don't have that problem, but here we have that. Okay, here we tell the linker that this position of the loader.s is the entry point of the resulting bin file. The output architecture is going to be i386:i386. And the output format is going to be f32 i386. Okay, what we do now is we need to select the sections from the different .o files. Okay, so we collect the sections from the different O files and combine them to new sections. And I'm not 100% sure what this actually does. This is just from from a tutorial that I've read. Okay, we create a new text section which contains, well, the text sections of the other files. So star point text star. Okay. Then it will also, before the text section, it will contain this multiboot section here. So star point multiboot. And I'm not really sure what this section is for. I guess it probably comes from C++. Okay, so this is a new text section. Then we put a new data section, which contains, I think this is for the construction of the global objects. You know, if you have global variables, this will make sure that their constructors are called. And we copy them. Okay, and it will also contain the data sections from the .o files. Okay, so the last thing okay, it's not the last thing. We also need to put the stack here, this section, this BSS section, into there. Okay, and now if we linked these files with this, the linker would not be happy, because at the end of when it's finished, it would have some symbols left over which haven't been put in the new binary file. So we need to tell it that it's okay that these symbols are left. So for example, here we have the comments. So comments can be removed. This is what we tell it here. If we have a comment, it's okay if it's removed. Okay, I think this should work now. Let's see. Line 18. Syntax error. There's a colon missing here. And also here. Okay, one small problem we have is it tells us the kernel main was not found. So the loader is trying to jump into kernel main, right? And there is this kernel main here, but the problem is that G++ has a different naming convention. So when G++ writes this into the .o file, it will change the name a little, and we just have to tell it not to do that, like this. Okay, so now the kernel is recompiled. There's this warning message again, and now the linking has worked. And here's your kernel bin. Okay, so let's install this. My kernel bin to boot my kernel bin. Okay. So make install. Now, and there's this my kernel bin in the boot folder, and now we just have to enter it in the grub-cfg. Okay. Okay, so this is a lot of stuff here. Okay, so let's enter this. Okay, so this is really easy. We just have to say menu entry, give it a name, let's say my operating system. And in here we just have to put multiboot / boot my kernel bin and boot. So save, quit, and this should be everything we have to do. So I'm going to reboot the computer now. Okay, you see there's the entry in the menu, my operating system. And there you see the operating system does what it is supposed to do. So there you have it. I hope you'll have fun with this. I mean, it feels really great to have your own operating system, doesn't it? And yeah, tune in next time. In the next video, I will show you how to install your operating system in a virtual machine, because I mean, you are not going to reboot your computer every time you have made a little change on your operating system. So you really want to have this in a virtual machine. So see you next time.